Welcome everybody to the April version of the schnee.semmelnar by OEGSL. Today it's the April version and it is in English. Finally, winter came back a little bit and we very much welcome live from Switzerland, EPFL in Lausanne, Johan Gaume. He is the, I would say, full-on professor now, as I think. I don't exactly know how it works in Switzerland, but he has a professorship and runs his own group, which is called Slab, similar to the guidelines that we are currently developing. It's very cool to have you here today. Johan used to be a pro snowboarder, so he's connected to snow. He used to work at the SLF and is still connected to the SLF. And one of the coolest things, what we're also going to see today in his presentation that deals with Supershear avalanches. A pretty American title because he also worked quite a little bit with Disney and snow, and I'm very, very curious what he's going to show us today, and we are very happy to have you here. Welcome, Johan, and stage is yours.
Thanks a lot, JT, for the very nice introduction. Welcome, everyone. Good morning, good afternoon. Yeah.
And maybe, John, give me a sec, because what I forgot, everybody who is in the Zoom, please use the chat. You can also raise your hand and post a question, but it's easiest to use the chat, so we moderate it. And same is on YouTube. If you have any questions in the middle or at the end, just drop your question and we're gonna try together with Johan to answer your questions. So, Johan.
Okay, thanks, JT, and yes, feel free to ask any question during the talk. No problem. So I'm going to talk about new understanding of avalanche release and so-called supershear avalanches, and how this can be important for the development of operational models for the evaluation of avalanche release zones. First of all, I would like to thank the colleagues at Slab, at SLF, and also in the Colorado Avalanche Information Center, Bertil, Louis, Lars, Grégoire, Alec, and Ron, who significantly contributed to the work I will show here, which is actually the PhD thesis of Bertil Trottet, but everyone here was also involved. First of all, I'm going to talk about slab avalanches. So the title, I said it was supershear avalanches, but I should have been more precise. It's supershear slab avalanches. And I mean, you are all very much aware of what is a slab avalanche. I will just recall very briefly at which process we will focus during this presentation. So here are the processes of dry snow slab avalanche release. So first, we have failure initiation in a weak layer, which is buried below a cohesive snow slab or multiple slab layers. We have some damage at the micro scale, and this damage may lead to the formation of a crack in the weak layer. And this crack may propagate across the slope, leading to the failure, fracture of the slab, and then the dynamics of the avalanche. And so in this presentation, I will talk mostly about crack propagation and slab release. This will be the topic. And of course, as you know, to study crack propagation, a very useful field test is the PST, the propagation saw test. And combined with some PIV techniques, so with these black markers and high-speed video, we can measure a lot of interesting things. So we can measure the critical crack length, and we can measure also the crack propagation speed. And where I would like to go with this is to say that concerning the critical crack length, there's been quite a lot of models that have been developed in the past, and let's say different theories, different paradigms, which are usually in conflict with each other. And I will talk a little bit about that. So the first failure model to evaluate the critical crack length is based on the work of Dave McClung in 1979 in this pioneering paper. And in this model, basically, the critical crack length decreases with increasing slope angle like this. but there is no critical crack length on slopes typically below the friction angle. So below 30 degrees, with this model, you have no crack propagation. And we, of course, know that this is incorrect, this zone. We don't know about this one, but this zone below 30 degrees is incorrect because we know from propagation saw tests, even performed on flat terrain, we know that we can initiate fractures even from flat or low angular terrain. And so to reproduce this propagation from flat terrain and also observation of remote avalanche triggering, there was the anti-crack model that had been developed by Heyerly and co-workers in 2008. And here, in this model, we have a finite critical crack length for low slope angle values, which is in line with what we see. But then the critical crack length seems to increase with increasing slope angle. And this also seems not realistic. This was shown by many different types of simulations based on finite element modeling, MPM modeling, so material point method, I will talk about this afterwards, and also DEM modeling. And so it seems that this is right. So we have a finite critical crack length for low slope angle values, but then it should rather decrease. And so apparently there is a kind of a conflict between these two models, but we will show, I will show you in this presentation that in fact, we may find a way to reconcile that in some ways. And so here, I'm showing you a simulation that we performed in 2018 with a new tool. So this is this material point method and specific mechanical models for the weak layer and for the slab, which allowed us for the first time at that time to simulate both the release and flow of the avalanche at the slope scale. And here, we actually simulated remote avalanche triggering. So this slope here is actually completely stable if I remove my snowman down there. And at some point, I release the snowman, a failure is initiated in the weak layer, it propagates upslope and leads to the release and then the flow of this avalanche. And what we did here is that we analyzed crack propagation dynamics, and I will show you how we did that in the next slides. But before, I would like to briefly introduce this new technique, the material point method, MPM. I will not go into the details, but what I would like to say is that in classical fluid simulations, for example, if you would like to simulate a river like this, you would have a fixed mesh, and you would not simulate the behavior of every, let's say, water particles. You would have a fixed mesh. You would look at what is going in, what is going out, and you would track the free surface. So that's what's classically done in fluid simulations. In solid simulation, on the other hand, we attach the mesh to the material, and then we really look at the motion of individual particles. And MPM is kind of in between. It's a hybrid solid fluid method, let's say. We have particles that follow the material in space and time, but we have a fixed mesh to calculate the forces and to basically solve the equation of motion. And that's really this hybrid character that allows us to simulate a lot of processes like fractures, also flow simulations. So we can simulate solids and fluids, let's say at the same time with this method. I will not go into the details. So this is it about MPM. And we validated the method by comparison to PST experiments. And here I'm showing you PST experiments performed on the 37-degree slope. You have the experiment here on the top and the model at the bottom. And here on this graph, I show you the vertical displacement of these black markers. Experiment here, simulation there. And we will see what's going on. What I can mention is also the color here. It's the horizontal position. So blue lines represent markers which are on the left, whereas yellow lines represent the markers which are on the right. And so now I'm running the simulation. I hope that my connection is okay and that you can see smoothly. We start to cut. First, we have a little bit of bending. and then the crack propagates, and we have the sliding of the slab. And as you can see, we reproduce quite well the bending phase, the crack propagation phase, so ACP here for anti-crack propagation. But we reproduce also what's going on after the failure, so the frictional sliding. This is another validation case here on the flat. This is not a video, this is just a picture, because on the flat we don't see much actually in this case. But as you can see, we reproduce very well the displacement fields, anti-crack propagation, but also the amount of collapse after the failure. And finally, one last case that can happen is that the crack doesn't propagate until the end of the column. We may have a slab fracture if the slab is not very thick and not very hard. The slab cannot sustain this crack propagation, and we may get a slab fracture. And you see that we can also, with this method, reproduce this crack branching mechanism. And so now I would like to go back to this simulation that I showed you at the beginning and analyze it in greater details. So here we were only seeing it as we would see a real avalanche, but I want us to look deeper at what's going on inside the weak layer. So here I will show you a top view of the weak layer. Our trigger, the snowman, is here, and the color is basically representing pressure. Black is low pressure and yellow is high pressure. And so let us have a look at this crack propagation phase. So you see it's very rapid. And I will pause the simulation at this moment. And what is interesting already at this stage, but you will see that's not that it is not the most interesting thing, but here we confirm that at the crack tip, we have large stress concentrations here in yellow. And below that, we have almost zero stress. So why do we have zero stress? It's because the weak layer is actually almost in a free fall state. The slab is in a free fall state. It's collapsing until it gets back into contact with the broken weak layer. And then we get some frictional behavior. But here, it's really the collapse phase where we have almost no pressure during the free fall of the slab. But what is more interesting here, and that's the topic of this presentation, supershear avalanche, it's related to the crack propagation speed. And here I'm showing you the speed. Yellow colors mean speeds larger than hundreds of meters per second that you see here in the slope. And this is quite interesting because on the flat, you see typically that the speed is around 20, 30 meters per second. And on the slope, it exceeds hundreds of meters per second. And initially, we were concerned about a potential error with the code, with the model, because we have never seen such high propagation speeds in field experiments. If you look at small-scale fracture experiments, so the propagation saw test, you do not exceed 60 meters per second. Usually, you get speeds between 15 and 60 meters per second. So we were really surprised, but then we also remembered that in 2014 at ISSW, Dave Amray and co-workers suggested, based on the analysis of avalanche videos, that crack speeds could be even larger than hundreds of meters per second. So we were wondering, is this an error in our code, or is this something real happening? So we thought, what's the main difference between our field experiments and real avalanches? But basically, that's only the scale. Here, typically the beam length is about 2 meters, whereas here we have scales which are 10 hundreds of meters. So we decided to perform PST simulations at a large scale. So from this view, it's hard to imagine, but basically you have to imagine that this is a slab of 50 centimeters, but the length is 30 meters. So the view has been shrinked so that you can see everything in the screen. But this is 30-meter long PST. You have one case on the flat on top here, and you have one case on a steep slope at the bottom, but the rest is exactly the same. The weak layer will be colored by its fracture, so red will mean fracture, and the slab will be colored by its vertical displacement, so it will show basically the collapse. So let us look at these PST simulations. What you can see, and I will show the video again, is that the case on the steep slope propagates significantly faster than the case on the flat slope. And we will see that this relates to something which is called supershear fracture. And I will show you more about that in the next slides. Here in this slide, I show you the crack propagation speed as a function of the distance. And the color means the slope angle. So different simulations, Bertil did different simulations for different slope angles. And what you see is that for flat and low angle terrain simulation, the speed is about, let's say 20, 25 meters per second, in line with what we see in the PSTs, in experimental PSTs. But above a certain angle, close to 30 degrees, we start to have a transition. We have a big jump in the crack propagation speed, and then it reaches speeds which are about 100 meters per second. And as you can see here on the right plot, you have PST crack speeds that you see in black. And here we have the speeds from the paper of Dave Hamre. So of course, this is not yet a validation. I will go to the validation case in the next slides. First of all, I would like to go deeper a bit into these processes of supershear fracture. And I also want to mention that it's not only MPM that is showing this. The PhD thesis of Grégoire Bobillet is on a similar topic, but using a completely different method, which is purely discrete, so in which you simulate interaction between individual particles. And he also reports the same phenomena. For steep slopes, you have a jump in this crack speed, which basically exceeds the slab shear wave speed. So that's why it's called super shear. It's because it's exceeding the shear wave speed in the slab. Another name that you can find in the literature is also called intersonic crack propagation. It's not supersonic. Supersonic would be higher than the P wave speed. Intersonic is between shear wave speed and a P wave speed. Let us have one more look. What is important also to see is what happened at the beginning of the simulation. At the very beginning, in fact, both cracks propagate at the same speed. But on the slope, something is going on after a certain distance. And this distance is about 5 to 10 meters. So we missed it in PSTs. We missed this transition because typically PSTs are shorter than 2 meters. So that's why we were not able to see that in this propagation saw test. And so here is, you see at this point, approximately, we have this transition. And so the typical crack length that you see in the PST is the one that you have at the very beginning that creates the propagation. So that's this one. Here on the flat, it's larger than on the slope. Then the crack propagates a little bit to another critical crack length, which is called the super critical crack length. I mean, that's how we named it. And I want to discuss this in a bit more details. This here is our supercritical crack length, ASC, as a function of slope angle. Here we see a case without much collapse in red. We have a case which is almost without collapse. And if we increase collapse, we basically decrease the angle at which you get this transition. So typically, if you have no collapse, then the transition occurs at the friction angle, about 30 degrees. But when you increase the amount of collapse in the simulation, then you get a transition before. And why is that? It's because when the weak layer is collapsing, you have no contact. So you have no frictional contact. It's basically a free fall. And this basically reduces the apparent friction of your weak layer. And this is something that has been shown by Alec van der Wijnen and co-workers in this paper here in 2009 experimentally. So this is a PST, and here he measured the effective friction as a function of time, and you see that at propagation, the friction drops significantly before you get actually to the crack face friction. And so this is what we see here as well. We have this critical crack length, a supercritical crack length that also decreases with increasing collapse amplitude. Yeah. And so what is the process here? What's going on? And it's something which has been reported in earthquake science, in strike-slip earthquakes. And it's a process which is called the Burridge-Andrews mechanism. So we have our classical crack that propagates. So the same crack as we have in our experimental PST, but after a certain length, we have a daughter crack that nucleates ahead of the main crack. And what is interesting to note is that at the crack tip here, we have a large normal stress concentration at this crack tip. So it's driven a lot by compression, but on the daughter crack, you almost have no compression. It's driven only by shear, as we will see in the next slides. So here I'm showing you more details about the stress states in these two simulations. We have the flat simulation on the left. We have the slope simulation on the right. Down there, I will show you the stresses. Normal stress is in green, shear stress is in red. And at the very bottom, I will show you the crack propagation speed, which is here normalized by the shear wave speed in the slab. So when it's 1, the crack speed is equal to the shear wave speed in the slab. And so, first of all, what we see, let us first look at the case on the flat. What we see is that we have large normal stress concentration at the crack tip initially, and almost very little shear stresses because we have no driving shear force and it's on the flat. And on the slope here, we also have large normal stress concentrations, but also large shear stress concentrations at the crack tip. And at the beginning, both cracks propagate almost at the same speed. And then if we look later, at a later time, when the crack has propagated a little bit, we will see that something has happened that created a speed which is larger than the slab shear wave speed. So I want us to go step by step, and let us first look at the case on the flat. If I go back and forth at this case on the flat, you see that the stress state at the crack tip is more or less the same. We still have large normal stress concentration and still quite little shear stresses. Now, if I go on the slope, let us have a look in more details on the slope. If I go a little bit later, it completely changed. Look at the normal stress peak. Here we have a large normal stress peak, and later on this normal stress peak has completely vanished. So we have a change from a mixed mode anti-crack to a pure shear crack. It's becoming a pure shear crack, which propagates at an intersonic speed, so a speed larger than the slab shear wave speed. Now comes the validation. So it's a bit complicated to validate.
Sorry, Johan, I would have a question to the slide before.
Sure.
Christoph,
yep.
The pattern of the two damages given in red in the upper two graphs.
Yep.
Why is it so different?
Okay, let us, it's an important point. So here, the first thing which is important to note is that the saw, in this case, we start to saw from close to the bottom. And then we see that the crack kind of goes to the slab weak layer interface. And on the flat, it stays like this. On the slope, we have these two branches. With the one at the bottom, it's a secondary branch. And we checked that this branch is induced by the fact that we have a rigid boundary condition. So we also tried with an elastic substrate. And if we have a softer substrate, we have the same result. So it's still super shear. We still have the same stress profiles, but this branch at the bottom kind of vanishes.
Okay.
So I would say that this is kind of numerical, the one at the bottom.
Yeah.
And in practice, as we know, also these weak layers are not perfectly homogeneous. So I'm not sure if these patterns, I mean, the true pattern of this thing, if we could validate that in practice with weak snow layers in the field. But yeah, it's a good point. We checked that it was mostly due to the rigid boundary condition.
Thanks.
You're welcome. And so the question was how to validate that. And so we already had an idea because Dave Amray made this study in 2014, and he did that based on the analysis of avalanche videos. But there is a but here. The analysis was made based on slab fractures. So they computed the speed by tracking slab fractures, but we are not sure if slab fractures really represent what's going on in the weak layer. So here we used another technique, which Johan developed, and it's a technique based on the change in pixel intensity. So the idea is to track slab deformation even before it starts fracturing. So it's basically tracking the change in light on the slab, and we assume that this change is due to the deformation of the slab. And so here I will show you a few videos in which this technique has been applied, and I will show you the results.
Drop.
So here we have Mathieu Scher, a professional Swiss snowboarder, who was also an EPFL student. And he triggers this big slab in valleys, and you see he has very solid legs, manages to escape successfully this quite large avalanche. And then here comes the analysis, frame by frame. And you see, you will start to see some colors here, which by eye is quite difficult to see. And only now you start to see slab fractures. So this technique allows you really to track deformation before the slab breaks. And we assume that this deformation is due to the collapse of the weak layer. And we use that to track crack propagation. And this is what is happening. We have the propagation distance here on the y-axis and time on the x-axis. And what's interesting to note is that there is a rather low crack propagation speed in the cross-slope direction, but the speed is very large in the downslope direction, 144 meters per second, which is based on the density measurements that we have for this case, larger than the shear wave speeds in the slab, which confirms this theory. This is another case here, an avalanche in the Pyrenees. A skier make a big turn and triggers this slab here. In all the videos that I show, there was no big injuries. And so again, the analysis, we have the big turn now, and then it starts to propagate. And you see slab deformation already way before you see the cracks in the slab. And this is the result, a very similar result. So distance from initiation point, time from initiation, and you see that the cross-slope speed is significantly lower, basically close to what we see in propagation saw test, actually, around 30 meters per second, whereas you have this intersonic supershear crack speed in the downslope direction. And this is the last case, which I also like, because in this case, it's not a downslope propagation, it's going to be an upslope propagation. So here is a friend of mine, Enzo Nilo, who triggered this avalanche in Val d'Isère. And we have a very nice footage, very stable, very good for the analysis. And it's also nice to identify the time of failure here when we have a big impact like this. And you see, I mean, the crown here is quite large. And again, he was not injured. He was pretty lucky in this one, also not buried because it's quite a large slab here. And here is the analysis. And here we look in the upslope direction, also in the cross-slope direction. And similar result again, 30 meters per second approximately here, and 125 meters per second in the upslope direction this time. And so this is based on avalanche videos. And finally, I would like to mention some work of my colleagues in Davos. This is work from Alec van der Wijnen and Bastian Bergfeld, where they did, let's say, the first 3D large-scale propagation saw tests. You have a 3D slope here, and Basti here will trigger this avalanche by stepping on the slope. And this will allow a more in-depth validation of this phenomena, because they will be able really to track slab deformation very precisely, whereas we do it from the snow surface in the previous validation that I showed you before. So this is really promising. The analysis of this avalanche has not been done in detail, but it shows super shear transition, which is good. So as I don't know if no, I'm good in terms of time. I think it's an intermediate conclusion. Just to say that basically we showed that we have a phase in which we have mixed mode anti-crack propagation for length typically below 5 meters, and after this supercritical crack length, we have a pure shear propagation regime, which is the one described in McClung's paper. So actually this work basically reconciles these two approaches. In fact, we don't have only one crack length, we have two. One is really needs this anti-crack mechanism to be described, so it needs the concept proposed by Heyerle, and the other one can be described by a pure shear model, like the one proposed by McClung. And this is very important in practice, because if we neglect, let's say, this phase of 5 meters, if we have to deal with large avalanches, hundreds of meters, and we neglect this phase, basically we can develop a pure shear interface model that would, in principle, be sufficient to model the dynamics of large releases. And so that's the direction we took recently, and we developed the depth average model. Because what must be understood is that the simulation I showed before are very long. They need a lot of time, right? It's several hours, days sometimes, because we simulate the weak layer, and it's generally very thin, so we need a very high resolution. And so we usually fill the slab and weak layer with particles, and instead of that, the idea will be to simulate the slab as columns of a certain height h, and the weak layer will be simulated as an external force, as a boundary stress, basically. And so we can simulate this basically on a simple lattice with a varying slope angle. And so that's that will really improve the computational time. And here is a little test that Louis Guillet has done in the framework of his master thesis. So here we have a PST viewed from the top. And here we start to cut. And then at some point the crack propagates, and it's in a depth average way. And here we validate that the critical crack length follows the analytical shear model, but also is in line with the full 3D model. So that's the case without slab fracture. And we did another case in which we allow the slab to break, and we also validated this based on a simple tension model. So that's the length at which we have the slab fracture, and you see we can simulate this en echelon slab fracture in a depth average way. And so here in this case, it's a particular case in which the slab fracture prevented the super shear transition from happening. For soft slab, we may not have the super shear transition. We need a relatively hard slab so that slab fracture does not prevent this transition from happening. Here is a little comparison between 3D MPM and depth averaged MPM, and you will see a bit how these fractures in the weak layer propagate. Oh, sorry, I started the wrong one first. I need to remove this and go here for the 3D MPM. So we see the weak layer here, failure in red, and this is slab deformation. And so you see it propagates a little bit like an ellipse. And this was also done in a depth average way. So that's a view from the top, and we initiate a crack by increasing the radius of a circular inclusion. And we also have a very similar behavior in the depth average model. And we also confirmed, based on this simulation, that the cross slope speed is below shear wave speed, and only the upslope, downslope speed is larger than the shear wave speed, as you can see here in this graph. That's the propagation speed in the downslope and the cross slope direction, and only the downslope speed is super shear, downslope or upslope speed. This is a last illustration in which we simulated also slab fracture. So we increase the size of this inclusion. We can imagine that it's a skier in the middle, and then we have crack propagation and the fracture of the slab with this particular interesting shape. So in that case, the slab fracture prevented the weak layer fracture failure to go up, but we may have cases where the weak layer failure may escape. And so this is what we have here. In a larger system, we initiate our failure, and then at some point it propagates. We have slab fracture, but then the weak layer manages to find a path, and then we have more complicated failure patterns, which are quite interesting, especially when we look at real avalanches. I mean, we see those kind of angles in let's say real photographies of avalanches. So even on quite homogeneous terrain, because we simulated that not on complex terrain so far, you can see these lines here and here, and that's very much in line with what we see here, and that's very likely related to the friction angle of the slab. And so in the future, we plan to continue the development of this model, and it could really help us to evaluate the size of avalanche releases, which could be useful both for forecasting, but also for risk management to get release zones as input of avalanche dynamics models. And this is it for this presentation. This is, let's say, a take-home diagram where you have the case in the slope with this supershear fracture and the case in the flat with the, let's say, anti-crack failure. Thank you very much for your attention, and I hope you enjoyed. And if you have questions, I'm very happy to answer.
Ooh la la, that was a lot of input. It was really cool. Thank you, Johan, for sharing your research and all this work of all the people you're working with, because this included, how many PhD theses did you just summarize in half an hour?
This was basically 2 theses and the ongoing work of a master's student who is doing the depth average modeling.
Okay. And concerning this last picture, is it correct to associate flat plane propagation, which is the shear wave, to the cross slope in the case on the slope?
Not necessarily. I mean, the speeds seem to be similar, but I think the processes are different. So it has been shown already for earthquakes that in mode 3, so cross slope, you cannot exceed the shear wave speed. It has been shown theoretically. What is limiting is the Rayleigh speed, so more or less 0.9 times the shear wave speed. Whereas on the flats, weak layer properties seem to have a large influence, at least based on the simulations that we perform. Elasticity of the weak layer is important. Thickness is important. Whereas for the large scale cross slope and down up slope crack propagation, it reaches a limit that becomes independent of the weak layer in some ways. And so that would be the difference. But in terms of absolute values, it's quite similar.
Because here in both cases, you call it mode 1 anti-crack on the summary.
Exactly. I mean, here in this summary, I didn't put the cross slope. So it would be mode 3. The cross slope here, if I would go in this direction, would be mode 3, which would then be different from this mode 1 anti-crack on the flat.
So the mode 1 is just the initiation, not the propagation. Or like in the sense of first critical cut length, second critical cut length.
In fact, here it's maybe I should have wrote mixed mode anti-crack, because it's not pure mode 1. We have other modes here on the slope. So what I wanted to say here is that it's a transition from a crack which is driven by collapse, by this closure, let's say, of the crack, to a pure shear mode. So it's similar mechanism before the transition in the flat and in the slope, and then it's quite different once you reach this crack.
Okay. And everybody feel free to ask questions on YouTube or in here, or to raise your hand if you have questions. I know this is Johan. Johan can be a little bit intimidating with a lot of content, but there's a lot of cool questions to ask, because I would like to go back to the Dave Henry slides and the theoretical speeds that you calculated in the beginning. You know,
You mean this one?
Yes, because here I was following you in the sense of that we are in the PST speeds, but this is modeled. Is this already measured, or is this only modeled?
Ah, yeah, sorry, I was a bit too fast. Sorry. This is model here in the middle.
Mm-hmm.
These are measurements. Yeah.
Okay, all the PST ones are also just from the model. So in the end, we can say in a PST, you never see supershear fracture.
You would if it was long enough.
So, so what about what is long enough? Like is the ones that Fabiano did in the Arctic with like, or I think Bastian did some like 20 meter PSTs. Are we long enough?
This is long enough, more or less. This one here. You need to be of the order of 10 meters. So the supercritical crack length can be about 3-4 meters long. Typically, it can be lower if you have a very weak layer. But typically, yeah, you need 10 meters, I would say.
So, and in the end, you can say a good summary would also be like the motivation was a little bit like, it looked like the measurements of Dave were a little bit like had too high velocities. They didn't really fit the measurements. And the idea was maybe to check if his measurements were correct. And in the end, you found out that the whole, you need the idea of the supershear wave, and then it actually fits again, yeah?
I mean, some of the speeds that Dave measured were particularly large. I mean, some of them were about 300 meters per second, which would be even let's say supersonic. So this would be, in my opinion, incorrect. But I think it's due to the fact that a lot of the videos were based on blasting experiments, and you know, that's why we didn't want to use such experiments. We wanted to use experiments in which it was clear. Triggered to be sure that there is not a large-scale influence of the blast initially. So I think that also we needed to confirm that the slab fracture was a good way to track what's going on in the weak layer. This we were not really sure, because it was really based on looking at where cracks would occur in the slab. And that's why we needed another kind of technique to validate that.
We have Ingrid with a question.
Yes, Johan, you said this opening angle of the crown fractures of the slope has to do with the friction angle, right? Did you study this influence? I mean, how does it, you know, what is this angle always the same? And would it open up more or close up or close again if the friction were higher, lower? Did you go into that?
So I think also slope angle may be important. So I think we need to go, we didn't do it yet, but we need to go into the equations. And I think it's a very similar problem than the one that we have in retaining wall. So, you know, this kind of 45 angle plus minus friction angle divided by 4, I think. So from Rankine theory, I think it's a very similar problem. So it's close to 45 degrees plus minus a function of the friction angle. But there is something which is very close to 45 degrees. And then you have another component in this angle, which would be friction dependent. But we didn't go into the equations yet to.
But sorry, Johan, this looks larger than 90.
I mean, this one, sorry. I mean, the alpha angle, I would say.
Okay, now I'm with you. Okay.
This is I think it's a very similar problem that we have in active passive lateral earth pressure 45 degrees angle of failure.
Okay.
But needs to be checked.
You see, I think this is the 45-degree angle of failure, more or less. Yeah. Okay.
Yeah, it seems so, but you see, you have other cases where it's not. I mean, also the views are maybe not the best. Here it worked not too bad, but also once the weak layer escapes from the sides and then it creates more complicated things, you may have, you see things like this and multiple steps like this. So we need to investigate that deeper. So what I showed is really the latest simulation of Louis, who is doing his master's work here, but we didn't try many configurations yet.
Yeah, it looks nice. I think it's interesting.
I would like to ask a practical question.
Mm-hmm.
So we learned now that there are two critical lengths we need to keep track. So the first is this critical cut length, and the what was the second? The supercritical.
Mm-hmm.
So you basically need a video to get that into in the field.
Sorry, what do you need?
In order to measure that, you need a video of your experiment, right? As Basti did that, or
yeah, but it's going to be hard to get back to the precise value, I guess. Maybe in the experiment of Basti, yes,
yeah,
that's possible. But from the videos, we cannot really go very precisely on the value of the supercritical crack length from the surface. But yeah, both are related in some ways. Huh? I don't say that you need to have both from let's say a forecasting point of view, because the lower the critical crack length, the lower the supercritical crack length in practice, because the ingredients are the same. It depends on shear strength, it depends on the shear stresses, and the other one has just an additional component due to the bending of the slab. But it's I think critical length is already a good proxy. There would be a relation between the two, a good correlation, I think.
Okay. But it is a proxy also for the size you can expect, right? So does critical or the supercritical length correlate with the size of the avalanche?
So basically, then you're right. If you compare the supercritical crack length to the length at which you expect the slab fracture, you can basically say, is it going to be big or small? I mean, that's something that we have tried here. For example, here we have two different slab strength. We make the same simulation, and you will see that in one case the crack stops, and in the other case you have this everything is breaking.
Yeah.
And so basically the criterion would be, it's kind of in the direction of what Ben has done also with the slab tensile failure criterion. You would need to compare the expected size of these fractures here to your supercritical crack length, and this would tell you, am I going to be supercritical or not? And you can say supercritical avalanches will be larger than the ones which are not supercritical. But so far, apart from telling maybe size 1, size 2, size 3, this it's going to be hard at this stage to define a criterion which will really tell you, okay, this is going to be this release volume, and you can just basically get some indices like this, probably.
Yeah, which would be already very cool.
Yeah,
and also would fit to our forecasting routines, because anyway we are using only indices in the order of magnitudes for describing the hazard.
But
yeah, that would be nice.
This relates a little bit to Bertie's question that he's asking in the chat, which is about the properties of the weak layer. So particularly if the thickness of the weak layer relates to the crack propagation speed, or which other, maybe you also have other properties of the weak layer, and which relates a little bit to the so we combine 3 questions at once, relates to the other picture that you showed earlier, where Christoph was asking where the failure of the weak layer happens, at the top, at the bottom. So maybe refer a little bit to the properties of the weak layer and how it relates to the crack propagation speed.
So in the supershear regime, once you have moved to this regime, the weak layer appears not to have any influence anymore. However, in the anti-crack mode of crack propagation, in this slow mode, it seems that weak layer strength, weak layer thickness, and weak layer elastic modulus is important. And I don't really remember in which direction it goes for the thickness, because we just started. I mean, Bertil started to make these simulations to check the influence, and it can go from, basically, you can reach the Rayleigh speed. Depending on the properties, you can find a set of parameters which will get you to this, let's say, 0.9 times the shear wave speed. But yes, the weak layer thickness, weak layer elastic modulus, and weak layer strength will influence the speed within a certain range. You cannot exceed this shear wave speed in this mode of crack propagation.
So to go, can you go one slide further? Because I think this would be the one. Here is back to this. You have these 2 kind of failures at the bottom, at the top. At the bottom, you say it's maybe even only numerical. But like, if you would extend the weak layer thickness to, I don't know, same as the slab thickness, which is not necessarily realistic, but maybe just to, what do you think would happen? Is the crack always on the top? Can the crack even, I mean, it makes sense that the crack or like the damage can only be at the top, no?
I think it will always go, I mean, in all the simulation that Bertil has done, it always can, because here we start to cut more from the bottom and then it goes to the top. So I think it would go to the interface most of the time. What could be interesting is also to add some randomness in the weak layer to see a little bit what would be the path of this failure. But actually we could try, because making the weak layer thicker is not a problem. It's making it thinner. If you make it super thin, then the simulations are super slow, because you need to have a resolution which allows you to fill enough particles in this weak layer. But yeah, we could try with something as thick as the slab.
Yeah, because maybe Christoph, you can refer to it on the practical level. I mean, if you have a really, really thin, nice, homogeneous weak layer, you always have a very good break quality in all the stability tests. But if the weak layer is, or like this would be this is actually the question. If the weak layer is way thicker, you also have way more chances for a rather resistant break. So the break quality is not that good in the sense of crack propagation. Is this correct from a practical point of view? And is it correct from a theoretical point? So practical point of view is Christoph's question, and theoretical would be Johan.
So theoretical would not work, because we would need, I mean, we would not get this roughness unless we bring additional variability, because it's a continuum method. So here we would need to bring this kind of notion of variability by, let's say, varying the strength of the weak layer and see what would happen in this case. And I would say that for thin weak layers, in fact, you would tend globally to a pure supershear regime most of the time. Basically, because you have sometimes avalanches in very, very thin interfaces where you actually, it's between 2 layers and you might not even have collapse at all. It can be between 2, just at an interface. And in this case, what we show in these simulations is that supershear regime would dominate.
And Christoph, what do you say from the practical point of view of stability tests and break quality?
I think from the practical point of view, it's not the the thickness of the weak layer, but it's the type of the weak layer, because these more irregular patterns you talk are closely related to depth hoar types, and they, on the other side, what I see when I dig profiles, have very often different types or different sizes or very mixed sizes. Some are large, some are small, which again refers to the theory that you have very random patterns of strength, because different connections and due to their different sizes. So I think it's more related to the type of the weak layer and not to the size.
Okay. So type in the sense of crystal size and crystal maybe even type. Yes.
It's a huge difference if you have a buried surface hoar, which is very, or it's very homogeneous from its type and size, and it's also very plate-like, versus a depth hoar, which is really random from its size and also its specific form.
Cones.
Yeah, cones and different grain sizes in a very small distance.
We are slowly getting to an end of this hour.
I think Ingrid is still raising her hand.
Yeah?
Yeah, it might not be so important. I just thought that does the absolute thickness of the slab also play a role? Because I just thought, I mean, if the slab breaks, it's maybe also a matter how fast does it break? Is the crack beneath the slab faster or slower than the slab breaking? You know what I mean?
Yeah, so for the slab fracture, yeah, definitely the slab thickness plays a huge role. Also, perhaps for the speed in this sub-Rayleigh regime, we didn't test it. We should also try to vary the slab height. As I said, you know, these are long simulations, so there are things that we kept constant for simplicity. But you're right, the slab thickness, the conditions for creating the failure in the slab will strongly depend on slab thickness. So that would be also interesting to test. Yeah.
Johan, Ingrid, thank you very much. Thank you very much for the questions. And probably if you have more, you can find Johan anywhere on the EPFL or by email or at any conference or at the bar. Thank you so much, Johan. This was really, really interesting. In the beginning, I thought this is going to turn out a little bit different, because I thought we're going to learn that the measurements are too fast and there's good reasons why it's not possible. But you convinced us otherwise, that crack propagation is actually very, very, very fast, which makes me a little bit sad, because as an avalanche dynamics guy, I was hoping that we are still the fastest. Now avalanches seem to move slower than cracks propagate. I'm not sure
maybe not for powder snow avalanches. You're still ahead.
But this is actually pretty close. So I think we have to go home and think about if the movement or the propagation is faster. So thank you very much, Johan, and thank you everybody for listening and being here this week again. And I think there's one more seminar coming up in May before we are going into the summer break, or at least it's going to be the annual spring meeting. But I think in the end of the month, there's a North American seminar still coming up. And stay tuned, enjoy the snow that is coming up, and very nice to have you here. Thank you, Johan.
Thank you for inviting.
Thanks, Johan.
Bye.
Thanks, Johan. It was really cool.
Thank you.